Okay, so thanks again, Yves, for giving the opportunity to come to Paris. And I'm actually not talking about sharks or rays, I'm talking about fish. And I'm doing this work on the bones of fish with a lot of collaborators. I won't, because of shortage of time, go into everyone, but as you can see, it's a long list. Before I start, even though you've heard some comments on bone, mammalian bone and other bone before, just to get us all to the same starting point, I'll just give a few comments that are directly related to what I will show later. And all vertebrate bones have a few same basic principles. And in particular, the building blocks, which are collagen type 1, fibrils, calcium apatite crystals, water, and some non-collagenous proteins. And also, all vertebrate bones have the same basic structural, architectural basic motif, which is the lamellar motif that consists of various arrangements of these mineralized collagen fibrils. And the lamellar structure has been described as rotated plywood, which implies that each lamella is made of several sublayers, and each sublayer contains mineralized collagen fibrils, which change sequentially their angular orientation. Then there are differences in the terms that these lamella are arranged. Some are arranged in cylinders, as we've seen several examples here, and this is one, for instance, taken from just a textbook of human bone. You'll see that one of my points in this lecture is that we're very anthropocentric, and we're talking mostly in bone about, or very often about human bone, and human bone is arranged in these cylindrical structures. These are the lamella, that's a central canal, and the lamella are arranged peripherally around this canal in a cylindrical fashion, but this is certainly not the only way bone can be arranged. This is from a horse, and it's again osteonal and cylindrical, but this is a brick-like structure from an alligator, and this is a zonal lamellar structure from a chicken bone, and there are many ways to use the lamella. Another thing that is common to all bones really is the bone cells, which are the ones that actually do the work. And there are three types. There are the osteoblasts that form bone, there are the osteoclasts that resorb bone, and I particularly want to draw your attention to the osteocytes, which are really have been in their previous career osteoblasts, but in depositing bone, they have buried themselves within the material that they have produced and have become embedded within the bone. And as several people already, Peter and John and others have mentioned in this lecture, in this seminar, they do a variety of things that are to do with modeling and remodeling. And they both serve as sensors, so they feel when the need is there to do this, and they also orchestrate then the procedure of modeling and remodeling. And modeling and remodeling are two very basic characteristics, very wonderful characteristics of bone. Modeling implies the ability of bone to change its external shape, its morphology, in response to different needs. So a tennis player, say somebody who didn't play tennis and starts to play a lot of tennis, the bones of his arm or her arm will thicken considerably, and vice versa. Remodeling is even more wonderful, and that's the process where when damage accumulates in the bone due to cyclical use, this area of damage, when it reaches a certain threshold, is completely removed and then replaced by new pristine bone that has no damage at all. And that, again, I think Peter said yesterday, the entire human skeleton is replaced within a few years. So if you look at this image, then you can see everything here. You can see the primary osteons, which are the same cylindrical motif, but produced de novo around blood vessels. You can see large resorption cavities. formed by osteoclasts, and then when these are filled by osteoblasts, they create these secondary osteons, and you can see that, for instance, this one is cut into the osteo neighboring to it, and same here, and this is the hallmark of remodeling. I'm afraid that every time I advance a slide, the second one comes, so I'll do, it's like a dance, 2 forwards, 1 back. Another concept that I want to mention is bone fracture. Fracture mechanics is obviously a very developed field, and I'm sure many people here are experts in that field. In the last 20 years, a lot of people who are dealing with metals and fractures in materials anyway other than biomaterials have gone into this field because bone presents a very nice and interesting example of a material that can resist the propagation of cracks. One of the things that make crack very common in bone is the fact that there are many stress risers inherently in its structure. A variety of cavities, from large ones for blood vessels, smaller ones for the holes where the cells of bone are sitting, and of course the resorption cavities. And if I just go back, I wonder if it let me go back. If you look here, you can see, and I should have mentioned this before, all these little black dots, they're osteocyte lacunae. So you see, bone is really characterized, all bones, and that implies applies also here. See, all these are osteocyte lacunae, and all these, and all these. So bone has a lot of osteocytes. It's the major, 90% of the cells in bone are osteocytes, and their function, as I say, is associated with remodeling. This is just an example of several images of bone with microcracks in them, and you can see this is quite a common phenomenon. Now, as I said, many people have examined, in terms of materials, the resistance of bone to fracture propagation, and various processes have been suggested. There are a few people who are leading this, Peter among them, and several groups in the United States, and microcracking ahead of the tip of the crack, bridging behind the crack, and maybe the most important process is crack deflection at a variety of anatomical structures within the bone. So how about fish bone? I've really worked until a few years only on mammalian and bird bone, and then I discovered that fish have a lot to say for them in terms of bones. First of all, diversity. We are mammals, that's true, and we are wonderful, but we only have a relatively small amount of species and lengths of evolution to have developed. Birds have even a shorter evolution, though most species. There's 30,000 species of fish with nearly 500 million years of evolution. So it just stands to reason that, first of all, there'd be a lot of interesting things to find there, and also many important lessons to learn. And just looking at some images of diverse fish, and I mean, this is just some pictures I took from the internet. The millions, well, not millions, but 30,000 different fish. I mean, this guy, I've recently seen him in Seoul in an aquarium, can weigh 1.5 tons. This doesn't weigh very much, but I mean, you can't not love it. This will play later an important role, I hope, in my lecture, but look at the extension that he has, kind of at this maxillary bone that he has here. So fish are everywhere. They're in the oceans, in the fresh waters. They live in, they can be small and large. They can live in extreme depths and extreme temperatures. So they must have solved a lot of problems, including the skeleton. Some observations about fish bone. First of all, fish bone has the same building blocks. So that hasn't changed. Collagen, hydroxyapatite, water, non-collagenous proteins. Fish bone has not been studied as intensively, but still it's been described as lamellar, and we have evidence now to suggest that's indeed the case. And one of the really interesting things about fish is that almost all, well, more than half of the fish existing today have a unique property that has been known for many years now, that they don't have osteocytes. That cell that's considered so important and fundamental to the performance of bone. And that raises questions. But even more interesting is the following question. If you look evolutionarily, I never know how to pronounce that word, in the direction of evolution, older fish, basal fish, did have osteocytes. It's only the newer fish that don't have them. So there has, in some point in evolution, at some period, osteocytes became expendable. And it's really interesting to understand why, because several questions arise. First of all, what was the reason that they became extinct, that there are no cells in those bones? Obviously, one would like to know, investigate the nanofeatures of the structure and composition and the mechanical properties of fish bone, because that hasn't been done very much. And then the two major hallmarks of bone, modeling and remodeling. Can fish do it? In particular, I'm interested in remodeling. Can fish remodel? So I'll just explain a little, describe a bit our detailed studies of structure and architecture of fish bone. And acellular fish bone seems quite boring at first if you look at the cross section. It's very layered, that is obvious. There are no osteocytic lacunae, no holes for the osteocytes because there are no osteocytes. And it's kind of featureless. We took this to the synchrotron with the help of Paul Zaslansky, and we looked at higher resolution at the structure, and it was completely featureless. In fact, when we took a cellular bone from one type of fish and an acellular bone, same volume of bone, and we looked at both of them and segmented them for the cavities, you see that the fish bone is absolutely littered with cavities for the osteocytes, and here there's almost nothing. It's a black picture. Then we looked at the flat surface of the same bone, of a different orientation. And there we had a bit of a surprise. I mean, it has been described, it has been shown in some papers, but again, it wasn't very intensively investigated. What we saw, and we saw this in many species of fish, just to be sure, is, we look at this bone, which is the gill cover, and we cut beams, and in what the image I showed before was of the thickness of the beam. This image shows the flat surface here, and you can see that it seems to be full with little, it looks like holes, maybe canals, about 1 to 2, 3 microns in diameter, and but it's completely filled with them. They are much too small to be osteocytic lacunae, and they're everywhere, as you can see. We looked at this with a scanning electron microscope at a higher resolution, and we were a bit surprised to see that what we can actually see that seems to be in these holes are bundles of collagen fibers that are oriented orthogonal to the overriding, let's call it lamellar layer. And you can see it here in even higher magnification. When we looked at this with backscattered electron microscopy, then these again look like holes, which implies that they are probably not mineralized, the collagen fibrils in there. Or at least that's my assumption that I'm trying to examine now. We next did a serial section view combining ion beam milling with scanning electron microscopy. This is the process again from the bone, preparing the sample and then cutting slices 10 nanometers thick. And when we get a stack of these, we get basically a sort of a tomography from the electron microscope with the resolution of the electron microscope, so at nanometer resolution. First, I'll show some examples when we did this to mammals, a human bone, mini pig, rat, and you can see that the fibers are either parallel, organized, or disorganized. There is always a small part of the lamella that is disorganized. When we looked at fish in the beginning, it looked the same, organized, disorganized. However, when we looked closer, we could see every about, I know this brings tears of joy to Jarrett when I mention these numbers, but these 1 to 2 micron diameter holes with what looks like unmineralized collagen fibrils, which are about 8 to 9 microns apart. And that's the reason we never, or almost never, see two of them. We have a few where we see the beginning of one and the end of another, because this whole thing is 10 microns. So this is our first clue that there's something unique about the structure, the lamellar structure, at least of the one fish species that we have looked in this detail. About mechanical properties, all right, so different ones that we want to look at. We so far haven't exhausted this study. We have looked at stiffness, yield, and we want to look at fracture, and we looked also at mineral content. Again, similar sample collection. Here, what we've done, and because this was a bit of an unusual finding, we have repeated this, and I'm showing you the results of the repeat. We've obtained beams by the same means, of the same dimensions, tested, prepared on the same equipment, tested on the same equipment on the same day by the same people, but from different species. So we have quite a few samples from dog bone. I work at the veterinary hospital, so I can get animal samples pretty easily. Turkey, human, horse, and then we have the fish. And there are several things that are apparent from these stress-strain curves. Fish are less stiff in the linear region. They all yield about in the same place. You'll see a table later, but it's about at 0.7% strain that they yield. These have a typical bone post-yield region ending in fracture. The fish have an extremely long post-yield region, and very often they didn't fracture within the limits of our equipment. Now, I know I'm saying stress-strain, and this is three-point bending, and I'm basing this on beam theory, so probably at larger strains this doesn't hold. So you can maybe look at this as force displacement curves, but the finding is still, I think, significant. As far as minimal composition, what we found was that, and that is also a bit curious, the ash content, that is the weight of mineral per weight of piece of bone, is the same in everybody, including fish, between 67 to 70%. However, when we did bone mineral density, we're using micro-CT for this, we found that in the mammals and the birds we get around 1.2, 1.3. This is also what is published in the literature. And for the fish we get usually less. I say 1, but it's usually really between 0.9 and 1 grams per cc. So lower amount of bone per volume, same amount per weight. This is the work of Mason Dean and John Dunlop. Mason has done a huge literature search, a meta-analysis of the literature, creating the sort of bone material space with mineral content, stiffness, and number of cells. And these are basically all the families of animal, classes of animals you can think of, and these are fish. And I think that this diagram establishes a priori something that has to do with the theme of the seminar, and that is that it seems within my little world of materials, which is biomaterials or bone materials, indeed there is a gap that is filled by fish bone. Does structure affect mechanical properties? I mean, we've spent the last 2 days hearing that it does, and certainly it does. So can we explain what we see with what we found structurally? Bone mineral density, the lower bone mineral density can be maybe explained by the unmineralized bundles. So can the lower stiffness, I think. And what would be really interesting and is the part of future studies is the effect of these bundles on fatigue, other properties, crack propagation, toughness. I'm not sure yet about the nature of these bundles, and structurally we have to answer a lot of questions of how these bundles are connected to the matrix and so on, but it promises to be an interesting field of examination, and it maybe hopefully ties in with Garrett's point about the combination of rotated plywood structure with gaps, some kind of a modulus mismatch of these, in this particular case, not holes, but unmineralized collagen fibrils. Now, just briefly, two sort of biological points of interest. First of all is, the equivalent is if a fish starts playing tennis, will its bones be thicker? So we can't teach them tennis, but what we did is we put screws in the gill bone, in the gill cover, and put a spring between them that applies, by the way, nickel titanium, so I want to fit in with the metallurgists. And so it applies constant force between the two screws. It's an orthodontic spring, and it applies constant load to this bone. It's an artificial loading situation. And you see they swim quite happily, they don't mind. And what we see is that in the area where the spring was, there was more bone production. These stains are injected into the fish and bind to the bone and show where bone is produced. And you can see that there's more bone produced in the area that was loaded. And the last question, which is really interesting, is to me is can it remodel, and or does it not have to remodel? So really, the two answers would be interesting. If it doesn't remodel, if it doesn't have to remodel, then especially in the large fish that live long, that would be interesting why they don't, and worth investigating. But even more interesting if they can, because if they can, they do it without osteocytes, and osteocytes are the ones that sense the need for and trigger the process of remodeling. So we try to look at a very extreme example for this of billfish. Billfish are those fish I showed in the beginning with the large nose. There are 11 subspecies. We looked at 5 of them. And the nice thing is, of course, that billfish their bone is acellular. This is a billfish in action. It's a huge fish. They can be 500 kilograms in weight. They can go 80 kilometers an hour in the water. It suggests that this long beam that they have tied to the front of them, when they turn, when they attack with it, when they use it, it will likely be loaded continuously, perpetually, cantilever bending maybe, and you would expect it to accumulate some kind of damage because it's mineralized bone. And therefore, if there is ever a fish that needs to remodel, it will have to remodel. So we with collaboration with Philip Mota from University of South Florida and his student Laura, they collected some bills, and we did some investigations in our lab. And this is just a cross-section of a bill. This is made from 500 microscope images tied together, just to give an idea of the general structure. You can see these two nutrient canals here. You can see a suture between the two sides of the bone. This is the end of another bone it's coming to an end here. But what I wanted to draw attention is to this area here, which is the next slide. And this is what it looks like. And the minute we saw this looked to us awfully like the bone of cellular mammals that have osteons. And just to make the point, this is a horse bone. The main difference is that there are all these cells here, but again, these circular structures with the central canal, you can see the lamella quite distinctly surrounding the central canal. At higher magnification, it certainly looks like it's remodeling because, for instance, this one cuts into this one, maybe this one cuts into this one. The first time I showed this, some people in the audience were not completely convinced. We took this to polarized microscopy, and I think this is pretty much a clincher for me because, again, this is a blue marlin, the bill of a blue marlin, and you can actually see what really looks like an osteon with lamella, a central canal, and this osteon definitely eats into this one and probably also into this one, and we have many images like this. So I realize this is not proof that they remodel, but it's suggestive. This is just a pretty image of the same, so I'm not going to spend much time on this. We then wanted to look at the three-dimensional arrangement of the canals in this bone. So we cut a cube. These are the three faces of the cube. This is the image we looked at before. This is a transverse surface. And on the sides, you can see that these canals are oriented primarily in a longitudinal direction. And this is when we took the same cube to a micro CT, and I'm just putting a horse near a blue marlin, and even better yet, if this will work. So this is in the billfish when it's segmented so that you can see the canals. There are some connections laterally, but the main orientation is along the length of the. And just for comparison, I'll show the same short movie with the horse. It's a bit denser, that is true, at least in this area, but the arrangement seems to be pretty similar. Another interesting thing, when you looked at the cross-section with backscattered electron microscopy, you can see that the borders of these structures are white, indicating they have a higher mineral content, which may confirm the hypothesis that is prevalent now that the cement lines, which are the borders of the osteons in mammals, are hypermineralized with some kind of function in diverting crack propagation. Looking at, I won't go through the numbers, just to show you a principle. These bones of the bill fish can be pretty stiff, like regular mammalian bone. All the bones of fish that were tested so far were much more compliant, but here we can reach 19 gigapascals Young's modulus in the axial direction. As you can see, the yield is same as in mammals, about 0.7%, and the stress at yield is also similar, and you can see that many of them, like other fish, we were not able to get to fracture, though some of them we did. Mineral, again, like in the other fish, is less than 1. Small sample size, but still it goes along with what we've seen before. So this is my last slide. My preliminary conclusion from this is that acellular bone, at least in the billfish, can remodel, and it'd be really interesting to know how it does it, although it doesn't have osteocytes. It may have an alternative mechanosensation mechanism. I don't know. Acellular bone can be quite stiff and relatively low BMD. And with this, I'd like to thank you.